Hello everyone and welcome into yet another live stream. And if you're grabbing a bite to eat all, then I'm just, I don't know. Stay here I guess. Hold on, let me just fix my headphones first. There we go. I always get gravitated to all these streams. Gravity of the matter at hand is such a beautiful pun. It really often goes unappreciated in my opinion. Hi the Kim, hi Droto, hi! I'm on time today. Yeah, so actually I'm streaming at a different time. I should really get a schedule, shouldn't I? Can you postpone the stream by 1.3 decades? I'm waiting for my pizza to finish cooking. Of course. Sure, we can write that there. Actually, let me grab by myself. But, whom did you vote? Whom did I vote? The one and only. The only person, the only reasonable choice. Ryan Gosling. My pick for the American president. Make it is literally the Tumblr sexy man. What is that? Hold on, I can't show you what is on screen yet because I'm looking up Tumblr sexy man. So I don't feel confident with. Oh, I see. Yeah. You know what, Happy? You're not wrong. 2 a.m. Wait, it's 2 a.m. right now? +7? +7. Oh, yeah, it is. Oh, I am so sorry for streaming this late, actually. Whoops. Back in the spooky month, yeah. That was literally Sans Undertale back then. Music, right, yeah. The live stream is awfully dry, wouldn't you say? I feel like music could really come in handy. How's the weather? Oh, the weather certainly is. I am feeling under it. Hold on, let me this, there we go, play. Oh, why is VLC like this? Why can't I just play multiple things at the same time at the very beginning? Why do I have to always include them into the playlist? So much work, for no good reason. There we go. Oh, you can't hear it, there we go. Should be better. So, make it please fix the date. Yeah, fine. You know I always start these streams unprepared. This shouldn't be news. Cheese flavored chips. I'm sorry. Cheese flavored chips? What? Oh, bite myself. Oh, never mind. I confused it with pizza. I thought we were eating cheese flavored chips pizza, and what an unholy creation would that be? Hi, Toby. It's raining heavily acidic tears, aka make its heavy acidic water, aka make its tears after the chemistry videos. What's context for the slice of pie? Oh, the whole bit of the slice of pie. Actually, I'm glad you asked because I haven't really mentioned it. It's kind of ruined at this point, due to, well, at this point, a year of neglect mostly. But the whole idea of the slice of pie, okay, was that we would have like a database of all the people who donated to charity, and then we would have like a pie chart of every single person, you know, their contribution, and then, you know, you donate to charity to get a slice of pie, get like a slice of a pie. You get it. It's funny. Originally it was on the Make It WTF. It still is there, technically. I still have a website. The only problem is the pie chart is broken. So there should be a pie chart right here, but it's broken for some reason. And so, whoops, that happens. So yeah, that's the context for the slice of pie. It's broken, and I don't have the money to fix it. I'm just waiting for someone to donate an irrational amount of money equal to pi. Yeah, we break the global banking system with this one simple trick. Donate an irrational amount of money. Or transcendental even. Would you be satisfied with 8 quintillion Zimbabwean dollars? Double it and give it to the next person. Make it in graphs because like ice cream and hot drinks. You have to excuse me, I'm yawning an awful lot. I am a bit. So what donation I thought was about promoting some pie company. Don't worry, eventually I'll obviously make a pie company called Slice of Pie, where I'll be saying pies and then, you know, pocketing the profit. Economists hate this one single site. One weird trick to... Trying to open the thing. What's the name? Fundamental Forces, correct? That was the name of the video, right? Oh, I finished all the animations for the chemistry video. Now all I have to do is edit it. The only problem is... well, I have to edit the video. So today we're just gonna work on another video. Because I'm working multiple ones at the same time. Because I'm doing fine. I'm doing well. This is gonna be just a typical make it stream where we're just gonna be chatting and I'll use me making the animation as an excuse to stream. Hi, the tomato. If you become a full-time content creator, would you start your own baking channel? No, I would just start a new series of videos called Bake It with Make It. And then I would just make food using extremely advanced chemical equipment. That would be such a banger series though. Talking about different chemical equipment. By just making food with... Oh, that's... Oh, not even chemical equipment, just different equipment in general. Oh, that's a banger of an idea. I would do it. But only if I become a full-time YouTuber. Make food with different chemicals? No, Nile Red already did that. Chicken soup, if I'm not mistaken. Nile Red already did it. No, Nile Red... Wait, what? Did Nile Red redo it? I thought Nile Red just, like... made pure cookies and like pure chicken soup. Bake it with Make It. Custom make it, making pasta also make well, chemicals. Yeah, just dumping lead into my pasta. It gives out a sweet taste, you know. Too bad because they drug gravity. Checking the mass. Except this quantized, so I guess we could pixelate this, that could work. Acid with citric acid, umami with MSG, sugar and salt. Yeah, but those are the basic flavors. When it comes to cooking, it's more about the more complex ones, like, you know, basically all of the ones dependent on your smell, not your taste. And those are much more difficult to replicate with chemicals. Only if you give the person the name of the pie. I love normal pie. Oh, I just cook a pie and name it Slice after everyone. That would be great. Is that wave nature something? Oh, this is gravity. This is meant to represent the 3 different theories for gravity. So classical, quantum, and relativity. And right here I'm supposed to... Actually, it should be a quantized field. So the only difference between quantized and normal is my blender just crashed. Cool. That's awesome. There we go. Never mind. We're fine. Is that right here, I need a single node. That node, it could work right here if I'm not mistaken. Or actually, we can just plug it in. Should be greater than... There, that's what I'm looking for, kind of. Boy, that looks weird from the side. That doesn't quite represent what I want. Why is life good these days? I'm gonna start thinking I need character development. There's a genuine psychological fear, if I'm not mistaken, where it's basically a fear of things going well. Because you're basically, you don't mind things going poorly, you're scared of things going well, because if things go well, then they can get worse. That's a genuine psychological fear. 20 pet roll pictures once I will blow. Found I have corona, I guess no school for next week. Oh, I'm so sorry, G. Which of the three kinds have the sea gravitons? Funny enough, it's this one. That's what I'm supposed to... Well, that's what I want to represent right here. But for it... Actually, checker texture. Oh, that's genius. That's because checker texture would just give us... Okay, so that's... There we go. Checkers. Exactly. Now... we do mapping like this, and we map the general like so, and we take value. We increase the size of the checkerboard, something like this. This is a cool way of teaching us something rather than showing us visualization videos. Oh, Kim, I agree, and actually, just give me one more day and I'll release a whole video on specifically that topic. That'll be the conclusion of the chemistry video, by the way. It's more about theoretical chemistry, and it will be about how schools are absolutely awful at teaching chemistry because they just tell everyone to memorize stuff instead of giving the intuition, theoretical intuition. Hi there, pigs, by the way. I don't know if I said hi, I'm so sorry. That makes sense when you imagine lag as a symmetric wave. One moment crashing down the next day. That's not how luck works. Dog that can explode. That is not how luck works. I'm done that. I am excited for that video too. The intro isn't quite as... I think I overdid it on the intro. I think it's not quite as funny as I initially imagined. Oh, you might need more subdivisions. This isn't good enough. Or you might need great scale. Like 8. And then what we want is we want to multiply them together, right? No, that's not what we want. Okay. You'll get what I'm trying to do, right? I'm trying to... No way, that's wrong. Oh, because I'm doing a checkerboard, that's not what I want. This would be more of what I want. I'm gonna beat satisfactory, good for it. Oh yeah, because... Well, I suppose that is a goal. Your voice is so chill. Thank you. That's all of the character development as Happy described. I'm playing a game. God, I'm the clown of entertaining it. Well, beats what I do. I'm just a clown. Period. Going to you when you find out how to objectively calculate the lag in any single portion of my life. You can do it with Schrodinger's equation if you want. You just need to solve the equation, the Schrodinger's equation, for all the particles in the universe. You're welcome. No need to thank me. Yeah, I'm not doing this correctly, damn it. So what I basically want is I want to take the checker texture, and then for each pixel, I want to color it in its entirety, either to... Hi Ninja. Oh, I can do it another way. Oh, that might be a bit clever. I don't know. I'll be honest, I don't exactly know. Let's set this to the right. Right here, we could do multiply by 100. So value multiply by 100 and then divide by 100. Well, not 0, that would be pretty... divide by 0 won't do much here. And then right here, seal. It is changing. Not quite the way I want to, though. Does that make sense? It's not seal. How about floor? That won't give me pixels. Oh! I did it. Huh. That's kind of the effect I was going for, actually. Cool. It's the clown entertaining me and also the entertaining God I'm entertaining things, so... Yeah. Clownception. And I'm using my forms for open school exam. Oh, that's great! I'm glad you're following in the chemistry one. And honestly, I'm still really impressed with the solution. I gotta say, I know I already mentioned it on multiple occasions, but I still think it's a genius solution. 0.23 underscore 660. Quantized. So quantized. What does quantized mean? Alright, it's right here we want text which says quantized and then quantized question mark, right? I don't know. I know, I'm just the guy who scripted the video and is animating it currently. How would I know? Hi the Remco. We're trying showing this equation, didn't have an understanding why I keep procrastinating at alternating the algorithms. You make all the cool animations in Blender? Yes, I do. Is the easiest in my opinion. Do I have perchance maybe a single just glowing? I do, that's lovely. That's gonna be unreadable, so we're gonna need a new material called text, which will look like this. And then in this text we'll take texture coordinate camera and just plug it in. That did not work. Not one bit. Okay, so that didn't work. Whoops. It was blue to red. Yeah, of the government website, I'm thankful. Yeah, lampposts tend to do things like these. If I had the nickel for every single time lamppost leaked important information of a government website, then well, I would have a couple of nickels. Actually, it would be easier if I just set this to 0, I guess, and then, well, no, it wouldn't. So right, so it's going blue. Oh, it's blue. Wait, that's good news, right? That should be good news, because that means combine. Because if that is blue, then what this basically means is that right here you have x to x. This is green. This is blue, which means that red is the only one changing. Oh, it doesn't help much, does it? Y is constant and Z is constant. Context would look better if it has shadow. Yeah, that's kind of what I'm trying to achieve here. I'm trying to make it so that the text is bright whilst the edges are dark, and that way it will be much more readable. Except I'm trying to do it in an extremely pointlessly convoluted way. I could multiply both of them together like this. Okay, so camera doesn't work in the slightest how I thought it would. That's good. Window? Hold on. Window. Well, reflection is the classic. Alright, so reflection has blue on the front and everything else everywhere else. So if we take this, if we plug them all in, for now, we have the color. Right here we can see that blue is on the front, which means if we plug the Z into strength, then the whole thing lights up. But the sides are dark. Oh, I'm a genius. That's exactly what I wanted. Okay, yeah. So now it has a little bit of a dark thing around it. And now I need to extend it somehow. The easiest way would be with a volume. Or I could just move it to the side. No, it's dumb. I'm so unbelievably tired for no good reason. I don't even have a good reason to be tired. But I need to save my strength, because after this live stream, I'm gonna finish a video. Yesterday I said nap stream. Tempting, I'll be honest. Tempting. Recently, I've been having a fair bit of bad dreams, which I really like. I do enjoy the catharsis of a bad dream. Yeah, this is unreadable. I mean, I could, in theory, I suppose, I could just change the hex of the color to something like blue, and then it's still completely unreadable. Makes sense. Yeah, because of the... okay, what am I trying to do? No, that's wrong. Control Z this, and just add the volume. Like a normal person would. Out of the 9 people watching, it's midnight. It depends when you're watching it, or where you're watching it. Time is relative, so is space. Said the more driving though. Hongshu. Voting for president. Simulation thing. I can't vote for the president. Make it who's winning the election. Well, actually, I can I go with that joke? I was so I had a joke ready, which I probably would have been funny, but nah, screw it. You see, I, as a European myself, illegally immigrated to America to vote for Trump's. Because me and all of my fellow illegal immigrants, we love voting for Trump, I gotta say. So, yesterday, that's why I'm so tired today, because yesterday I just went to America, illegally, to vote for Trump. So yeah, that's just what I do. That's the only election joke you're gonna get out of me. No politics. No politics. No politics during the election season. I don't have it in me. Seagull hair guy. Who's this trampoline guy? Why he's like what so much? Okay, that's it. No, let's focus on the video. We're not talking about the American politics. You can talk about European if you want. I don't know much about Asian, unfortunately. That's one too many continents for me. That's such a good-looking planet. Oh my goodness! Look at this thing. I am good at what I do. And modest too. It's truly amazing. Do I have volume? I do have volume. There we go. Oh, that volume might be a bit too light. I see. Okay, so how about dense volume? The viewer count almost doubled. Oh no! There's 19 funk music background planet spheres. That's all you need in life, honestly. Wait, why is this multiplying? What is this multiplying? Oh, I forgot this was like more... Okay, so each time I just click on the shader tab, the entire blender gives up. So that's not good news. Just increase the density of it. Okay, I can, but it's gonna look absolutely awful. So instead, we need to increase density right here. We could do it with addition, like this, and then we could squash it down, like so. And then we could increase the size of it all, like so. And then it's actually a bit more readable. Just a bit. Now we can make the whole thing darker, like so. And there, it's actually fairly almost readable. Politics feels boring. There are a grandpa who had too many drinks and now just relaxing some with dementia. Actually, it's quite the opposite. In my opinion, it's America basically baby right now. No, it's in Europe. It's quite the opposite. Here's the thing: American politics is House of Cards. European politics is Game of Thrones. European politics is just so complex. How long did it take you to get this good at Blender? I tried once, was completely lost. 4 years, I think? 5? I'm not certain. 4 or 5 years at this point. Oh, quite the opposite actually. We'll parent this to this. There we go. Keep transform. And then now we can just have quantized at the top, which should be a bit more readable now that it's with volume in the background. Happy you literally described Joe quitting for the elections. No politics! No! No! Don't make me talk about politics on stream. What's titration? It's when you... I was gonna say some sort of joke, but I'm just not feeling it today. It's the exponents. The exponent of the exponent. I kept trying to understand after the time travel shenanigans. Yeah, honestly, at this point, it's too confusing. Like in the EU, you can't even tell what's canon or what's legends. It's so unbelievably confusing. But you know, Europe had multiple writers over the years, so that's what you get when you just mix people up like that. It's a mess. But to be fair, okay, I get it. Europe is a bit inconsistent, like they had a lot of writers, but come on, in America they're just doing completely random stuff at this point. The writers nowadays are so lazy, just completely making things up with no justification for why they happen. So apparently, I don't know, Elon Musk all of a sudden is paying millions of dollars for people to just like pledge their allegiance or something. Like, come on, get realistic. The writers are honestly just making stuff up. I mean, I get it. It's meant to be fiction. I understand, but you could at least make it somewhat realistic. Try to be serious then. The beer party. Oh, the beer... I love the beer party. Don't you dare say a mean thing about the beer party. I love the beer party. I'm all for the beer party. Beer party is great. Unironically, it's Austrian, right? Come on, in Austria you have FPO, who's actually winning. That's upsetting. It's upsetting me to call. Make it, you're more than a third of the way towards 100,000 subs. I am, aren't I? That looks like the flag on Naked's desk. Oh, it's uncanny. It looks practically the exact same. Injection dependent. Imaginable quanta. Send out the quanta. Alright, so what we need right here is 2 particles. Hi there, lamppost! Buckshot from optics is just so good, getting absolutely... I'm not gonna read that, lamppost. I can't... Lamppost, how am I supposed to read that, okay? Exactly. What the heck? I still remember times when lamppost just didn't feel like comfortable enough just saying stuff like these, and at this point it's just normal. It's just normalized at this point. Lamppost joining in saying stuff like, I'm taking backshots from optics, or I'll raw dog this shit till I get... No, I'm not gonna read that. Whoa! No. I choose not to. I don't wanna. Make it, you're smart enough. Depends. So how do you go from a first person to third person life? Third is my true self. Third person is true self. Those in the epic laser death machine pigs video, they look AI generated. That's how you know you've reached the the Iron Man level of machinery, when you're building something that just looks AI generated just because of how many cables and parts and complexity is there. I don't know if I can show the images, or actually at least one to get my point across. May I? Says those things so normally. I know, Kim, I know. I am fully aware. They're in the public channel. So this machine is so unbelievably complex that it genuinely... Actually, no, the other pic was better for this. Yeah, hold on, the previous one. A while back. There we go. This just looks AI generated. Making the corner looks a bit small today. Well, I'm just trying to be the bigger person, alright? My brain's delayed. I can relate that today. I'm just not feeling it. Is that the rail cannon? Actually, you're not that far off. In a sense, yes. Exactly. It's no. It's not a rail. It's not a rail cannon. It's an ionic cannon. I can hop in VC and explain the experiment idea. Oh, please and thank you. Oh, of course. I would love that. So hold on. Let me just. There we go. It's so complex, though. My goodness. Change going location. Hi, the flame. Hi.
Hello.
Let me pause the music, and there we go. So, the machine. I mean, you didn't really mention what it does exactly, but that it's a lot.
So I'm just very happy that I've done an experiment now. So what this is basically a simpler version of the machine I'm building.
Simpler version.
Okay. Yeah. Because this was like a first version, and what they're gonna do with this first version is they're gonna attach more stuff onto it and make it more advanced and do some more difficult stuff.
Yeah, you know,
because they're changing it into a new thing, I have to make a copy of this basically.
Yeah, I mean, better. I get it. Actually, the first time I saw this picture, I was like, oh, that looks a bit simple. To me, it seemed a bit, seemed basic, right? There's not much going on there, so yeah, it makes sense. I mean, okay, I get this. Okay, so here's the thing. I know I have the gist of an idea of what this is supposed to do, right? Because you did explain it multiple occasions. So this makes sense to me. This makes sense to me. What's all this?
Okay, that whole big section is where the ionization takes place. So I think the sample goes in. You see that sticky out bit on the left, like the bottom left. I think the sample goes in that, and then it gets ionized somehow. I'm not sure yet. And then it gets shot. You see the tube that then comes out towards the top left and goes into this other stuff that's being built. That's where the whole time of flight thing happens.
Wait, this right here? Should I give you a stream on
that
Discord
whole tube
too?
is the time of flight.
Should I give you a stream on Discord? There's no delay.
Yeah.
Okay, hold on. There we go. So hold on. This is where the time of flight happens?
Yeah.
Oh, then I have no idea what this is then. Never mind.
So yeah, that whole section, I'm a bit confused as well about why it's so big. Because it should just be the sample goes in, you ionize it. So maybe it's going to have multiple sample holders. I'm not sure. But essentially, the sample is going to go in there. And in the middle of that, so you see where the tube comes out, kind of before that, where the tube crosses with this main section, there are going to be some electrodes which can then accelerate the sample into the tube.
I'll be honest. Okay, so you know how sometimes you explain something to me, and then I get it, and then and then it turns out I don't actually quite get it, and then you explain it again. Then I'm like, oh, I see. That's where I got lost or whatever, right?
Mm-hmm.
Now that you actually shown me the machine, I still don't understand why it's like this.
Okay.
Actually,
Go on the whiteboard thing. So I'm going to explain how this stuff works. So, I will start by drawing. What colors should I use?
There we go. Jam space whiteboard. Is that all like? Whoa, it is. Lovely.
Okay, so our sample starts somewhere here, and it goes this way, and here we ionize it.
Mm-hmm.
And so now the sample is ionized, and it gets in here somehow. This whole section, I'm not entirely sure about how this works just yet. So this is my weak point.
Yeah, but the point is it's ionizing it. That's the point.
So the sample goes in, we ionize it, and it gets to here. And so what I've drawn here is 3 electrodes, and so these electrodes look like one looks like a donut. I've drawn that circle really badly. So the second 2 look like donuts.
And this is basically a railgun.
Yeah.
The railgun so dog yes, it is a railgun in part.
So this one has a negative charge because this is our repeller electrode. And this one has a positive charge because it's our extractor electrode. And so, when the particle's here, particle's negatively charged, right?
Yeah, so this one is... So, hold on. So this one is pushing away while this one is pulling forward.
Yep. And then this third electrode is our ground electrode. And that just... You know what a ground is. So that's just 0 potential on it.
Mm-hmm.
And I think that's just so that the electric field then doesn't spread out this way. The electric field is then just kind of cancelled here. And so then past that point, there's no electric field, right?
Right.
Does that make sense? So
yes, I think it does.
Over here, we've got negative charge. Over here, we've got positive charge. But then once we're past this, there's no charge in space.
Makes sense.
Okay. And so then our negatively charged ion travels this way. And this is our whole time of flight section.
Where the entire measurement of velocity at the point happens.
It doesn't actually happen here. But what happens is it separates by
Oh yeah,
mass.
because you. Okay, yeah. Never mind then.
Because
Right.
if we go back to the electrode here,
Yeah, then you
we're
want.
applying a fixed voltage, and so that's applying a
Yeah.
certain force onto the particle.
So basically, if you have a bunch of different particles, all I know there's going to be a bit of an oversimplification, but if you have a bunch of particles that all start at the same point, and they but start at different velocities. Then if you give them like a meter to travel through, then after a meter, they're all gonna be at different points.
Exactly.
And so that's how you can measure the velocity with a distance. So here, the distance would just be proportional directly to velocity.
Yeah. So they separate by mass.
Right, so here's the thing. Hold on. First of all, hide the turbulence. Also, Doug can spell two geniuses as they walk. I wouldn't say that. This is just Flame explaining to me something that he does on a daily basis. Also, the hide the lawmaker, by the way. And also, one more thing. Argon's outdated that particle shooters are public now. Oh, this isn't. This is just an ionic railgun. Normal research stuff. Something I totally need for research. Okay, so here's the thing. Here's what got me so confused, I believe.
Mm-hmm.
When I saw this picture, oh wait, in order to paste it in, I need to like do it in some sort of dumb way, isn't it? Because
you have to download it and then upload it into this. I think. Yeah.
So dumb.
It's
Hold on.
really
How do you
bad.
upload even stuff?
Oh,
add image. I see. Okay.
Yeah.
Save image as, save whatever, and then there we go. How big is it gonna be? Uploading image, right?
I think you can shrink it anyway.
Okay, great. So let me just find a nice place for it. This fits, I suppose. Here's the thing. Actually, it's nice. It is color coded. So that's nice. All right. So if green,
I will color code this image.
So if I understand correctly, yeah, this big part is the green and yellow ionization. Then this little tube right here is where. Oh, inside the big tube.
Yes.
Oh, yes, that's where I got confused.
These have to propel it, right?
Here's the thing. When the... okay, it makes sense, actually. Now you mentioned it that way. It does make sense. But when you mentioned the magnets, what I imagined is like, a big... So magnets plus this, right? In my mind, this needed to be a big tube because of the magnets. And it also needed to be long because of the whole, time of flight thing. Mm-hmm. And so that's why I thought it was this one. I thought it was the big one. But it's the iron.
No, it's actually just the really thin tube because all you need in there is a tube for it to travel. So you just need length and nothing else. There's no other property you need.
I don't know how familiar you are with Warhammer 40k.
Not familiar.
Yeah, there is a section. There's in Warhammer 40k. There's something called Cult Mechanicum, which is basically like techno shamans or whatever, where they basically work with this hyper advanced, futuristic, mind breaking technology. Except they have absolutely no clue how it works, and so they basically just trust in the machine spirits. So the reason why this is so big is because, from my understanding, the reason why this is so big is because this is witchcraft, and so we just kind of. It was kind of built by an arcane sorcerer, and so it has to be this big, because how would you shrink magic, of course?
Yeah, I am going to find out more about how this section works, because that's the bit I don't understand yet, is the actual plasma source and ionization. Is I know like you can generate a plasma, which will ionize it, and you bombard it with electrons, makes it negative, right? But like I don't know the details of what's going on.
Also, another thing. Okay, so right now, this makes sense.
I've only drawn half of the machine, by the way.
Of course. Of course you did. Also, this is the simpler version, right? I'm sorry. Every now and then, it just hits me that all of this is an actual image. It's taking genuine, mental effort.
In this background bit, this is the one I was working with today.
Oh, I see.
So this one actually has, I think this. Let me make it smaller. This is our green section, and the electrodes are in here somewhere. And
this tiny tube right here is the traveling one.
Yeah, the time of flight is along here.
Oh, I see. Wait,
What have
actually,
I color-coded it? Color-coded it green. Yeah.
there's
Time of
one.
flight is this whole section.
There is one thing I'm curious about, and I know that the answer will probably not be all that interesting. The question, but because, well, it's probably just because of abstraction and systems or whatever. But why are there so many controls for this? It's like so
I
many
guess
cables.
because you
so
have
many...
to be gauging the pressure in each like section. So you need pressure
I see.
gauges for every section. Because, for example, you might want to depressurize one section while you're still putting something into a different section. So you have gates to close them off. But you have to be checking the pressure in every section because everything needs to be ultra high vacuum. You also have controls for, I guess, the plasma generation, turning on the electrodes. You have the electrodes you turn on here. You also have, I haven't drawn them, but you also have a couple extra electrodes up here. I'm trying to remember the configuration. It's really small now. Hang on.
The thing is, I know what...
You have a couple more electrodes here, which like refocus the beam. I can't remember exactly what they were. But these correct for the beam defocusing here. This like refocuses it and makes it all, I can't remember the word, collimated. These collimate the beam. So you have more electrodes. Then you have more electrodes down here. And the laser and your VMI detector. And you need to time the laser to hit the thing and the electrodes to activate at the perfect time, which is all happening within a fraction of a second. So there's just a lot to control.
Yeah, the thing is, I know the question I want to ask, but at the same time, I know I very much shouldn't ask it, because the question I actually want to ask is, well, it's not really a question. I just want to point to every single cable present and basically ask you what it's for.
I don't know.
Yeah. So
I look at these cables. I'm like, what is going on?
I'm just. I mean, because I understand that they're all there for a reason, and they're all like to probably either to control like one specific measure or to measure that measure, or connected to, well, or they're all connected to something for the sake of obviously either checking the information or inputting it. But
let me send a picture in the channel. This is as an example of some of the stuff we're controlling.
I just love how casually, by the way, you are doing an ionized cold. Oh yeah, I've seen it. Yeah.
Okay, you've seen that. Yeah. So, I sent it earlier. Okay. This is like an example of a lot of the stuff that's hooked up to the electrode, to the wires and to the
thing
electrodes.
is, I have seen it.
All of these, if you see the bottom left where it says like Einzel, VMI, TOF, these are all electrodes which we're controlling the voltage of with these knobs.
The thing is, I have seen it, but there's one thing that was actually kind of curious to me, is that when you have ion, it's obviously all of them is not a single thing.
Yeah.
There are multiple controls. I don't know how in depth I can go with this, or I also love
don't know too much. I just know they were fiddling with the knobs, and I asked, what does that do?
By the way,
and like the PhD student, she was fiddling with the TOF knob, and I was like, what is that actually doing? And she said, it changes the voltage on the electrode for the time of flight. And I went, okay, that makes sense. So yeah, that's all I got from that.
By the way, I absolutely love the mouse pad with a periodic table. That's first things first. And second, I have the exact same. This is the exact same tape as I used when I was having my chemistry mental breakdown when making acid. But apart from these two, okay, I suppose this makes sense. By the way, I am so gosh dang, like. It's a very specific feeling you get when you like technology in general, and you see this hyper specific science equipment for something that's so, I don't want to say mundane, but Like,
I
a
mean,
whole
I will not
panel,
lie. I
control
was sitting
panel.
there in awe at how all of this is coming together.
Yeah, it's basically
Yeah.
like Chernobyl control panel to the whole reactor, except you just have it in the room and you're walking with it and you'd actually know what it
Yeah.
does. It's incredible.
I
And
like how the chat just devolves to random talks
oh yeah,
as
I
soon as
know, I
I'm
know.
here.
Oh no, that's actually because Turbulence joined in and Turbulence trying to convince us that Britain
Okay.
is real, so, Also, how
Yeah,
did
it's not. This
Gabriel?
lab was actually just taking place. This lab is in the void. We just spawned in.
It's just an underground
Yeah.
facility.
Should I finish the drawing of the machine?
Oh, go on.
It was like half drawn and you started asking questions. I'm like, well, I haven't finished it.
Oh, go on. So sorry.
Can I rub this out? That's not. How do you rub it out if the white isn't white? Look, the white isn't white.
Listen, I know that.
Is there an eraser?
Oh, I
There's no.
don't see crap
Can
it
I
out.
select it?
I think so.
Okay. There we go.
That's so dumb.
Okay.
Arrows.
So it travels here. Detector, I guess, can be purple. So we have a detector here, which detects, funnily enough. So my size is way off. Good enough. Okay, so the ions hit this detector.
Right.
And what this detector does is it gives us a graph that says, oh, at this time something hits it, and then here something else hits it, and then here something else hits it, and here something hits it. So this axis is time. This is just intensity, I guess. So this detector spits out a graph that tells us, oh, we've got these different peaks because our sample is separated by mass, and so we're getting different things hitting the detector at different times.
Actually,
does that make sense?
Yeah, actually, bit of bad timing. Dolinsek asked, what is he researching though? Could I attempt to answer, and then you can double check if I understand this properly? So, what I'm understanding, Dolinsek, I'm not the one researching. I cannot stress that enough. That's Flame. This is gonna be second-hand, actually, explanation right when the expert is sitting with me in voice chat. I'm good at my job. But basically, if I understand correctly, there are all of these ionized molecules right here. Ionized, basically, in this case, what matters most is that they are charged, they're affected by charge, and you have electromagnets accelerating them forward. And then these electromagnets are going to accelerate different molecules at two different speeds. So this is right here we accelerate these molecules, then they accelerate, then they hit the detector at different times, and so depending at which time the molecule hit the detector, then that means it accelerated to a different speed. And so the research is basically about the charge to mass ratio, was it? Because charge tells you how quickly they will accelerate, and mass is inversely proportional because it slows them down.
Yeah, that's correct. We say mass to charge ratio, but yeah.
Mass to charge. Then I got backwards. So I got a... okay, I'm just ever since...
I will say, what you've got half of it, but you're actually missing a huge portion of what the research is.
Well, now it's time for the actual explanation. I just wanted to double check my understanding. Go on.
No, you've up to this point, you understand it. So this graph that we get is the mass to charge ratio, essentially, because each of these peaks tells us the mass to charge ratio of the sample we have has hit this. But we don't know what the actual charge is. We can just guess based on all of this.
Right.
We can guess most of it is going to be molecules that have one negative charge. But we might get some that have two negative charges or three or whatever. But we only care about the ones with one for this example. So we get this graph, and can I select it? If I just do this? Yes. And can I deselect this? Yes. Okay. I'm going to move this off to the side for now.
Just off the page.
Okay. So we get this graph, and the thing to remember with this experiment, is that every second, today anyway, we were doing this whole thing 20 times a second. So 20 times a second, this thing gets ionized, shot through, and it gets yeeted across, and we detect it, and it pops up on the screen. Okay, so this whole thing happens 20 times a second.
Right.
But this has only told us the mass to charge ratio. And how do I get back to drawing? Okay, there we go. It's only told us the mass to charge ratio, but what we're actually interested in is, I mean, I'm surprised you didn't notice, but we haven't used the laser yet. There's no laser here.
Oh yeah, I completely forgot about the laser. I'll be honest. It's not that I did not. I just completely forgot about that. But I kind of got sidetracked with the railgun.
Okay, so we shoot a laser this way, and it technically travels through. But what we care about is it hits it. So the laser hits our particle, our molecule, and what we can do is, based on our graph, using the detector of the mass to charge ratio, we can time this laser to hit whichever one of these samples we want. Do you understand that?
Yes. So basically, to each peak, we now have a corresponding laser, basically.
Yeah. What we have to do is we have to add like a time delay to the laser shoot, to the laser like activation, to make it hit whichever one of these we want.
Right.
But because we know the time it takes for each of these to travel, we can time the laser to hit each of these. And so the laser hits one of these, and what we have is we have our molecule, which has an electron attached to it. Because if you remember, it's negatively charged, so it has an electron on it, which it doesn't really want to have. It kind of wants to get rid of the electron. And when the laser hits it, you're giving this plenty of energy to yeet this electron away. And so what happens is the electron then travels in a random direction. Not entirely random, but it travels in a direction. Do you understand that?
Yeah.
So we're giving it energy to kick off the electron.
Right.
And the thing to remember is there is an activation energy to kick this electron off. And if you give it more energy than the activation energy, then the electron gets kicked off with velocity, right? So it's like you have, an activation energy that's this high. If with your laser you give it this much energy, then that means all of this.
This would be the velocity.
Yeah, this is kinetic energy.
So basically, if you had like a graph of the laser energy, and then this would be the activation energy, then this would be the graph of the velocity of the electron. To kind of graphical interpretation.
You mean this up here?
Right, or this up here.
Because when you're down here, you're not giving the molecule enough energy to kick off the electron in the first place.
Oh no, yeah, I mean, this is basically energy of the, so the further, well, no, hold on, no, I'm doing this incorrectly. This is energy of but that's energy of the laser itself, and then this right here, red, would be velocity. So if it gets hit with the laser with energy equal to this activation energy, was it?
Yep.
To this activation energy.
It's not actually activation energy, but I just called it that because you know.
Okay, so if it gets hit with the laser with energy lower than the threshold, then it doesn't actually. Then it still sticks to the ion.
Yeah. Yeah.
Right. So that's why. Before this point, the velocity would be just 0.
Yeah.
All right. Yeah, I get it. Okay.
Okay. Yeah.
It's quantum mechanics, by the way. That's not even theoretical chemistry at this point.
I mean, quantum mechanics is theoretical chemistry.
Oh, I know. It's just that fun fact. Actually, my first, not first, the second quantum mechanics video I've made. One of the examples of quantum mechanics I used was specifically this. It was the activation energy when hitting electrons with photons.
Yeah. So with this, it's actually called electron affinity, not activation energy, and I think the name is quite explanatory because it's the affinity this molecule has for keeping the electron, right? Like if it has a high electron affinity, it really wants to hold on to the electron. So you have to put more energy in to get rid of it. But if it has a lower electron affinity, it's going to be quite easy to kick this electron off.
Right.
So I'm going to draw something and you're going to go, wow.
Okay. Wow.
Can you tell what I've drawn?
Of course. Okay. All right. That makes sense. I mean,
So,
it can make sense for two reasons. I actually don't know which one it is exactly, but I have two theories why.
mhm.
No, am I supposed to say the theories? Because okay. So,
I'm interested in seeing what you come up with.
all right. So, is the ion charged because of that electron? Like, without the electron, would be neutral.
Yes.
So, if the electron gets kicked off, then this molecule will just keep going and it won't care about the magnets.
Yes.
Oh, so that is the reason why the magnet's
Yes.
there.
So now, why do I have electrodes here?
Because if it doesn't get kicked off, then it will just get accelerated this way and it won't make its way to this sensor.
That's. I mean, you are correct, but in that case, why do I even have the electrode here?
Well, it's because we want to only measure the molecules that got that we know the activation. There was an affinity. I'm just gonna call it activation energy because my brain is too tiny.
Yeah, that's fine.
So that's why we're going to only measure the molecules which activation energy is lower than the energy of a laser right now.
I get what you're saying. You're wrong,
Oh,
but I get what you're saying. The thing is, what we've done is we separated by mass. So we're already this laser is only hitting a certain molecule,
right.
right? Or it's a bunch of molecules, and the laser will hit like one or two of them. But it's hitting a specific molecule. Like the bunch is all the same molecule, right? So it doesn't matter whether the electron gets knocked off or not. If you remember, electron has like a negligible mass,
Right.
especially for chemists. We do not care about the mass of an electron. Whether this gets its electron kicked off or not, it's still gonna hit the detector.
Okay. No.
Right.
I mean, what I meant is that if the electron doesn't get knocked off, then the magnet's gonna pull it away.
Yes, that is true, except imagine the magnet isn't there for now.
Right.
They will hit the detector regardless what happens. So the question is now, why put the magnet here?
Well, I'm assuming to pull the charged ones away. No.
So, I'm gonna tell you it's to pull the electron away.
Ah, that was my theory number 2. Damn it, I should have stuck with it. When I mentioned two theories, the first one was the ion, the second was the electron. Damn it.
So it pulls the electron this way, and this hits a detector.
Of
Yeah,
course
another
it does.
detector. So what are your theories on this? What are we doing? What is
Honestly,
this detector for?
the reason why I went with this one as a second is because, well, this one would be for electrons then, right? If it's pulling them
Yes.
away.
Yeah.
I have no idea
I
why.
guess technically the ions where the electron doesn't get knocked off will travel this way, but it's probably calibrated so that the electrons aren't gonna. So that the mass is gonna be too heavy for it to do anything.
So this obviously is for the electrons, but I'll be honest, I have no idea why.
Okay.
Absolutely. No clue.
So it's quite complicated. It's kind of complicated. Okay. So when our electron gets kicked off, let me move these. How do I change this?
Oh, there's fireworks in the background.
Yeah.
Still going on. My goodness.
Yeah. Okay. When the electron gets kicked off,
Right.
for now we're going to say it travels in a random direction. Right.
Mhm.
I'm just drawing a bunch of arrows. So immediately after the laser hits it, our electron is traveling with a given velocity. Right? And you can imagine if you were to average out all the electrons, then you'd have a sphere of electrons traveling outwards. Does that make sense?
Yeah, if it's going the random velocity, then it's gonna be.
Yeah. So if we have our electrodes, what we do is, we transfer this sphere of electrons out this way. The whole sphere moves this way. And on our detector surface, the sphere hits it as a circle. Does that make sense?
Yeah, projecting a 3D sphere on a 2D surface.
Yeah. And so the thing to I'm trying to figure out how to explain this. So when when this sphere gets moved, the sphere is still growing in size as it travels this way. Can you imagine that?
Yes.
Yeah. So right here it's a point, but as it travels, it gets bigger and
I mean,
bigger.
it makes sense because if you have an electron that's traveling right this way, perfectly to the right,
Yep.
well, let me make this a bit bigger, perfectly to the right, then these magnets, electromagnets, close enough.
They're electrodes.
Yeah, these electrodes. That's the word. That's the word I was looking for. These electrodes will have a negligible effect on it. If it's going to the right this way.
Actually, no, they will have a big effect on it, but you're right that it carries this momentum it has. So whatever velocity it's at,
I mean,
it will still
negligible.
keep moving that way.
I mean, negligible
but
to the
it's
right.
also moving this way.
I mean, negligible to the right. So on
Yes.
only the x coordinates, they won't really
Yeah.
change much because this one
Yeah.
is pushing to the right quite as much as this one's pushing to the left.
Yeah.
Okay, so it makes sense. It's
Okay.
growing. Then.
So yeah, so what this does then, what this whole layout does, is you get an image that's a circle, but the position on the circle tells you what velocity the electron had and in what direction.
Okay. Yes.
Does that make sense?
I think so.
Because if it's like on the edge of the circle, it had
a lot of velocity
really
to
high
the
velocity
right or the left.
horizontal. Yep. Whereas if it's in the middle, it was probably going
So,
this way or
wait,
that way.
So it's basically this, except with an electron in a sphere, not a line.
What was this again?
That was
I'm trying
the
to remember.
that was measuring the velocity of points by letting them move through space. So in this case, they won't be moving through space forward, except to the right and up and down. So it's actually this, except on the exact opposite coordinates. So right here, it was only about forward, not caring about right or up, and right here is just, and right here is just
it's-
right or up.
Yeah, it's the inverse. Yeah.
Okay.
I mean, whether it's in the middle will tell you which direction it was moving in. Like if it's in the middle, you know it was moving either that way or that way. You know, like towards or away from the detector.
Yeah, so it tells you basically right, left, up, down.
so-
in this case,
so-
I mean forward,
yeah.
backwards as a line.
Essentially, this is configured in a way where the position tells you the velocity of the electron. The velocity that the electron had here.
Mhm.
Right? So that's what happens. And so now if I pull up an image, can you see there are two images where there's like two blue circles on the screen.
Is this the? Oh, yeah, I see it. Hold on, let me
Yeah.
save it. An image. This one. It's uploading so slowly. It's all coming together. It's almost as if it's a real thing.
Yeah. You don't understand how excited I was when I saw this pop up on the screen. I was like, man, this is the theory I've been reading for 4 weeks. Now it's actually there on the screen. I can see the electrons on the screen. Like, so yeah, this image, and you can see it looks like a sphere because it's a 2D projection of a sphere.
That's so unbelievably awesome.
That's really, really cool.
That is so unbelievably awesome. Oh my goodness. Oh, and you can actually see right here, unless I'm wrong, in the middle it's darker, right? Oh, that's way too big.
Yeah, in the middle it's darker.
Which means that, wouldn't that be, oh wait, hold on, never mind. That makes sense as a slice of a circle. That actually makes sense. That edges would be brighter in the middle. That's so cool though. Oh my goodness.
Really, really cool. I was so happy when I saw that. And the reason there are two circles here is that the left image is, I think, an average of like, I think it was like 20 pictures of this experiment. Was it 20? I don't know. Yeah, the left one was a small average, and it was collecting a bunch of these left ones and adding them all up to make the right image. So the right image was our sum after running it for like 5 minutes.
Oh, I see. Oh, that's so awesome.
So it gets higher resolution the more times you do the experiment.
That is so awesome. Wait, is that the entire machine?
That is the whole thing.
Ish.
In simple terms, yeah.
That's amazing. Actually, okay, so here's the thing. By the way, I'm so sorry, Dolinsek, for not answering the questions you had so far. I've just been a bit, well, I'll be honest, focused on the explanation. That is cool. So, wait, so could you, like, now that we get how the machine works,
yeah,
could you answer the question of what is actually the purpose? Like, what were you trying to...
So the purpose, the info you're getting is the velocity of the electrons. That's the raw info you're getting, right? Like, I'm getting this image that says the info and the velocity of the electrons.
Wait, so if this part is giving you mass to charge...
Yeah, so the whole reason for the mass to charge thing is only so we can select one of these peaks to then point the laser at.
Okay, so this one is giving you mass to charge per molecule. This one is giving you the electron affinity, was it? My goodness, my brain is small.
It's not actually, this isn't giving you the activation energy. I guess it kind of is. But
it's activation
you don't need
energy.
To work it out.
Oh, I don't. Okay, then I think I was misunderstanding the purpose.
It is a property. It is tied to the activation energy. You're right. But what you could actually do, I'm going to ask you something. See if you can figure it out. So in the video, I think I sent 2 videos.
Yes.
Okay, I sent those 2 videos. Oh, I sent 3 videos. Okay, you can see there's a video where I said yellow laser versus red laser, and I've sent 2 videos.
Yeah.
Can you see the laser in those videos? It's kind of hard to tell. It's like the flashing light.
Yeah, one of them is yellow. On the second one, you zoomed in. One of them is yellow, the second one's red, yeah.
Okay. What do you think happens when I change it from yellow to red?
Well, I'm assuming you changed up the energy of the laser, because it changed up the wavelength.
Correct. So what happens?
Well, what happens is that with red is low energy, if I'm not mistaken, right?
Yep.
So if there are certain molecules with the red laser for which you would get nothing here because it won't activate, that's not enough energy. However, when you add more energy, so you use the yellow laser, then you will get the electron sphere, I know what to call it, which means based on that you can get the energy required to knock that electron off.
Yes. You're entirely correct, yeah.
Ah, feels good to hear, I'll be honest.
That means, I'm pretty sure, you don't need to use this to find the activation energy, because you can just change the wavelength of the laser until it stops working. And then you're like, oh, well, that's the energy it needs, right?
Oh, that's actually what I meant. That's what I meant by it's telling you the activation
energy. Oh, okay. Right, but that means that this whole image is pointless because all you need is to see if the image is there, not any info about the image.
That's actually what that's actually the thing that doesn't click with me.
Okay.
That's what I'm confused about.
One other property I will tell you is the size of this sphere will also change based on the frequency, the wavelength of the laser or frequency.
Oh, I see.
Does that make sense?
Yeah, it's because when you hit it with even more energy, then right here we had the graph, but we removed it. Then it will have even more velocity.
Yeah, our excess energy is all kinetic energy, so we give it more kinetic energy.
The more, so for example, if instead of a yellow laser you use the blue laser, then this sphere would have just been bigger.
Yeah.
That makes sense.
Yes. Okay, so that was another thing that I just wanted to point out because it's an interesting observation to make. It helps you understand it a bit more.
Wait, so this is basically... Wait, so is this just here to check, like, what molecules are you hitting with the laser?
Yes. It's to check what molecules you're hitting with the laser, but you're also... The whole point of this is to separate it out into these different molecules. because you don't want the laser to just hit all of these combined.
Yeah, right. So you want
Yeah.
to hit obviously one specific because otherwise you're
Yeah.
just gonna get a mess. And
Yeah. So
then-
it's to hit one specific molecule.
this is so awesome, by the way.
Yeah, I find it really, really cool.
That makes sense now to me why my previous explanation was lacking so much, because yeah, this is basically just the preparation. This is basically
Yeah.
just prepping the molecule. And
Yeah.
this is the actual experiment, or rather this.
Yeah.
That is so cool, I gotta say. This is,
So yeah, your question about what info you get from the image, I'm not entirely sure. I need to still
yeah,
understand.
but at this point I get it. This is just
Yeah.
it makes sense now that I understand that this is just the preparation.
Yeah.
Because then the info is basically obviously the info is the electron scattering or that.
Yeah, it's telling you the dynamics of the molecule. And you know when I said let's assume that the electron gets scattered in random directions?
Yep, it doesn't.
It doesn't get scattered in random directions. Yeah.
That's such a chemistry thing. You know when this is random, it's not. It's
But I
never
mean,
random.
but you could see for the sake of explaining it, it made sense to call it a sphere, right? And then yeah,
Yeah, it makes sense.
yeah.
This is
So yeah, does that all
so
make sense?
cool.
now?
This is so unbelievably cool. Oh my goodness. That is so awesome. Okay, I'm having trouble. The only thing says that's cool as fuck. I'm having trouble saying anything of the consequence because, like, all my thoughts are just, oh my goodness, that's so awesome.
Yeah. And so this is what I'm building as well. This is what I have to build for my master's project.
That's so.
I think
Also,
the purpose for today's experiment was mainly to just give me data and actually like let me do an experiment. But now he's sent me off to go and analyze the pictures. So I had to run it through some software, get some kind of info from it, and so I guess over the next week I'll be able to tell you what this picture actually gives us.
at this point,
But
I'm
in
just.
short, it tells you about the dynamics, the excited state dynamics of the molecule. Because you're trying to figure out how does this molecule behave when the light hits it? Like, what does it do?
Actually, hold on. Two things. First of all, bye Kim, bye, have a good one. Second of all, Dolinsek said, bro, I'm literally studying this right now for an exam. It's cool to see someone
Wait,
actually
what exam?
doing it.
What exam is that? What?
This is so. I mean, for me, the reason why it's so specific is because I haven't actually made that many videos on quantum mechanics. If there's only two, if I'm not mistaken. In the second one, the specific example I used was a photoelectric effect, if I'm not mistaken,
Yep.
which knocks off the electron depending on the wavelength of light because of the energy.
Yes.
And to see, someone using specifically that mechanic to then measure the scattering of the electrons, it's just.
Yeah.
I love so much how basically in most science experiments, the biggest challenge isn't like getting the data at the very step. It's the biggest challenge is getting the data, right? So basically, in this case, what you want is the electrons after they've been knocked off by themselves, and then you have to go through the process of making an industrial-sized, basically molecule accelerator, the ionic
It is
railgun.
literally a particle accelerator. Yeah.
Yeah, a particle accelerator ionic railgun, in order to just then at the very end have the electrons. I'm honestly at a bit of a loss for words. This is just wow.
I do just find it really cool, and I've spent weeks reading about this. This guy's given me so many books. He's like, oh yeah, read this and this and this and this. Now, I've been reading a bunch of stuff and being like, man, when am I actually going to see it happen? And today was the day, and I'm really, really happy that I've seen this.
I am so happy. This is. I'm sorry. You need to give me a second, okay? I need a second. Okay. Now coming back to this machine. Okay, so right here it's accelerating this way. And then
So
is
just
this
to
meant
clarify,
to?
this isn't the machine I used today.
Yeah, I know. This is
one
the one
being
that's
built.
still being
Yeah.
built. So
Yeah.
is this the place where the electrons will be separated off?
You mean where? Oh, sorry, I forgot to tell you, but this section, the this second section, can you see where I'm pointing?
Uh,
Up here.
I can. It's in the middle for some reason.
Oh, it's not. Okay. This section
Right?
is, we call it velocity map imaging. That's what this detector does. Velocity map imaging.
Yep.
Okay, so you can call it VMI if you happen to remember that. You might just forget. I don't blame you, but just call it VMI. It's a lot easier to call it that. So, are you asking? Where was the picture? Wait, over here. Are you asking if this is where the VMI happens?
No, this is where it gets separated off to then go to the, so that then electrons can go to the VMI and molecules can go to the spectrometer. I don't know.
Oh, okay. So you mean where those electrodes are, where the second electrodes are? Because you got the
Yep.
first electrodes here. I think it's further down here. It's actually going to be over here somewhere.
Oh, I
Because
see.
we've put a lid on this. You know, there's a lid here. Actually, actually, no. I think this is it. I think this is. I think you are right. Actually, I think this is where it hits because these holes here. We put a bunch of holes on here, and one of these holes, I remember he told me, is where the laser goes. Why is this so massive? The laser goes into here and out this way. So I think this is where it happens.
That makes so much. It's. I mean, I'll be
I'm not
honest.
entirely sure. I might be wrong. It might be a bit further down, but I'm pretty sure this is where it happens.
I mean, it would make sense because it is a big part with multiple like connections and.
Yeah.
This is just great.
Yeah.
A particle accelerator. Casually walking the particle accelerator.
Yep.
I can't wait to hear, by the way, what data this actually, the electron actually gives you.
I need to. That's the
I'm
two things I
curious.
need to learn now. Is I know, I understand. So if I zoom out, I understand all of this really well, but I don't understand what this is, and I don't understand exactly what this is doing.
I mean, I'll be honest. The ionization is kind of. I
think the ionization can be interesting.
I mean, it could be interesting, but I don't think it's.
I need to understand the logistics of how is the sample getting here, and how we make, like.
Yeah, that makes
what are we
sense.
doing?
It's just that in terms of like this experiment, the ionization seems like the least interesting part.
I mean, yeah, you can literally just bombard it with electrons, and it will become negative.
Exactly. I mean, I'll be honest. I'm still curious why it's so big. That's like you can't just have a part this big in the machine and have it do
weird.
something boring.
Especially considering the other machine, you can see it in the back here. It's not that big.
Yeah, something off his foot. Also, I just want to see this.
Can you bring in the photo? The first photo I sent today.
Yep.
Can you put that in? But also,
this one.
is your name Dolinchek? I don't know how that's pronounced.
Dolinsek.
Dolinsek. Also, what kind of samples I analyze? Today it was just a random sample for me to get data and to test that a certain thing was working.
Yeah, so this is basically like a test to a machine that's meant to be a test. So you're building a machine that's meant to be the smaller model to then build the actual machine, and there was the test of that test machine.
The one I'm building is not meant to be a test machine. The one I'm building is meant to be the actual one to replace this one.
Oh no!
Because this one is being transformed into an even better one.
I mean the built one.
Else.
The built one is the test, and the building
the built one is So I was testing using this built one.
Yeah, so that's what I meant. You were testing the machine that's meant to be a test for the bigger machine that's yet to be built.
But what I was testing today was just I think it was think it was just ethanol. I think they said the sample was ethanol with argon, um, which is really boring.
I mean, I gotta say
Um,
the difference between like the expert and the noob. Like, I'm just setting ethanol on fire for a video, and you're just
Shooting
ionizing it,
lasers,
showing it
yeah.
through a railgun, shooting lasers at it, and then
Um,
checking the electrons that scatter off.
but yeah, so the sample today was just random. But the objective is to use it for astrochemically relevant molecules, which is a fancy word of saying molecules we want to understand whether they can be formed in space and what they would do if they were formed in space.
Yeah, the electrochemistry in this case is surprisingly underwhelming.
What do
It's
you mean
more
by electrochemistry?
not sorry, astrochemistry. Both words sound
Yeah, the
about
astrochemistry is more of the applications. It will be interesting. Like once we have the data on certain molecules, it will be like we can then say, oh, based on the electron affinity of this and the excited state dynamics, we wouldn't expect this molecule to form, but this one could do this reaction, and stuff like that.
Actually, I'm trying to figure out. Okay, so astro. Do I keep saying electro? Astrochemistry is just there for the molecules that you will analyze. It's not like the.
Yeah, it's not related to what I'm doing very much,
I'm looking.
except that what I'm doing tells us so much detailed info about what a molecule does that it's useful for
Yeah.
astrochemistry.
I'm just trying to figure. I'm trying to piece together, or well, not piece together. I'm trying to make a semi-educated guess on why the electron data. Like what specifically?
It in short, it tells you the excited state dynamics of the molecule. Which is just it's really complicated. When I was drawing, I'm trying to remember. When I showed you that like energy map thing where it was like a 3D plane with dips in it, where lower energy is like dips in the energy plane.
Yup.
It's like that, but for a molecule. And so if you imagine it has those planes, but it has loads of them overlapped on top of each other, and they're all crossing through each other. And what happens is when you give the molecule energy with a photon or something, you excite it into a higher one of those planes, and then it drops back down, it crosses through, and eventually it finds its way back to the bottom by switching through all these different maps and finding its way back down. So that's the kind of info you're actually getting from this.
I see. Okay, so yeah, that's way above my pay grade. Yeah. Okay.
It's also right now. I have no idea how this, how the image that we get on this translates into that stuff.
Yeah, the thing is, for that I'll just have to wait because at this point making a guess would be just silly. Even making a guess, still, this is so I'm just I can't even. I just can't even. The entire machine makes so much more sense now to me.
I mean, I was trying to explain it to my mum over the phone earlier, and I was like, this is so much easier if I just draw a diagram.
The thing
And
that's
so,
problematic in this case is that this is something that would be really difficult to understand without knowledge of theoretical chemistry or quantum mechanics. Like normally when you're explaining a single concept in any field of science, in my opinion, you can explain it in terms that even someone who doesn't understand that field, they can get the idea of what the concept is about. But in this case, it's just a combination of concepts. So
yeah.
in order for someone to understand, they would just need to have at least like a basic understanding of quantum mechanics.
All you really need to understand is, maybe this energy concept is a bit difficult, but all you need to understand is that this accelerates negative stuff, and here your electron gets kicked off and it's negative, so it goes this way. That's like, and then this velocity thing might be a bit difficult to understand, but the main stuff that's going on, I think you can get it through to most people.
Oh no, I meant like the concepts are easy. It's just that as a whole. So in order to explain
Okay,
this, you just need to explain. Well, I guess ionization in order to explain why it needs to be charged for the whole charge to mass ratio thing. Then explain this, which also would be pretty simple, and then this. This one actually, I don't think this is all that difficult to explain. I just always
Yeah,
like to
no.
imagine it as two magnets. Like you need a certain
it's
amount
like
of
magnets,
energy to
it's- yeah.
separate them, but once you separate
Yeah.
them, all that extra energy is gonna convert into velocity of the second magnet. Also, I know it's a bit unrelated, but for the chemistry video, I do have a section after I explain the energy of orbitals, energy of bonding, the statistical aspect of reactions. At the very end, I do have like the conclusion thing I'm quite proud of, where I just mention like, so yeah, atoms behave in obviously different ways from classical objects because they're not classical objects, they're borderline quantum objects. However, once you account for that behavior, this is just normal physics. So, for example, reactions depend not only on the kinetic energy, so temperature, but also depend on the angle at which the molecule hits another molecule, the orientation which they hit, and you can literally just think of them as balls smashing together.
Yeah, you can make a physicist understand this with no chemistry knowledge. Yeah.
Yeah, it's because it's not even that you can think of them as balls smashing together; they are just balls smashing together. That's
I mean, they're not balls, but yeah.
yeah. I mean, I am oversimplifying with balls,
Yeah.
obviously. They're just objects smashing
I just
together.
wanted to answer because Dolinchek was asking, so the ionization is non-destructive. In this case, what we have is there are different ionization methods for different experiments, and some are called hard ionization and some are called soft ionization. And whether we call them hard or soft depends on how aggressive they are, like how aggressively they ionize stuff, basically. And in this case, we're using hard ionization methods, so these are quite aggressive. But the thing is, we use small molecules, so they're not going to break apart. But if you try to use a bigger molecule, like for example a protein or something, this would rip apart the protein. The protein would just break off because it can't handle that energy. It would break into pieces, and then what you'd actually get on this spectrum is you'd get the different pieces of protein that have gone through because they're separated by mass to charge. So in this case, it's a hard ionization method, but because we use small, simple molecules, they can't. They're not going to fall apart.
That makes sense. For the big machine, actually, for the big machine, will you still be using the soft method, or?
I think I'll still be using the hard method. I mean, he said plasma, and plasma is a very hard.
That sounds pretty hard.
But if I, oh yeah, you pulled this picture in, and then I forgot to actually talk about it. This one over here.
Oh yeah.
So this is a different angle. Can you tell that this is the same machine that I was talking about that I used? And
hold on, I need to take a closer look first. I think so.
This is our green section, and then this is where the time of flight happens that way, and the laser is back here somewhere, and the VMI is up here.
Right.
Right. So this is all here, and this this screen is the screen in that video. So I was standing over here taking that video. Right. You can see he's building stuff over here. And what this is stuff that's going to get attached to this machine. And so this is a whole extra section that's stuff is going to go through here and then go to here and then get directed that way. Right?
Oh, I see.
And so this is what I meant when I say that the one that's been built is going to get turned into something else, and the one I'm building will do what this whole section does. Because the one that's been built, he's going to add this whole section to it.
Actually, wait. So this is added on the very beginning, right? Oh, that's a bit.
Yeah. So instead of putting in the sample in here, the sample is actually going to go off around this way somewhere. Like.
So wait, is this going to ionize it?
What this does, and this whole section here is for separating by isomers.
Oh, I see.
So you can separate specific isomers, which is insane.
Wait, hold on. No. I don't want to gloss over that. No. Because this is isomers. Let me double check isomers mean what I think they mean. First of all. Okay, yeah. How is it separating off by isomers?
I'm trying to remember because he showed us. And
remember how I don't know how many I don't know how many streams ago was it, but remember when I was complaining about how
you were
isomers
like, oh, isomers don't do anything.
You mean to tell me that you were working in the same lab as the same lab as a machine that literally separates them by isomers, and you didn't?
He hasn't built it yet. This is like part.
I suppose for the point.
He's waiting for another part. I would have actually worked on this for my masters. Except the part that he needs is only going to be here in like February, so I'm just not working on this.
Damn it.
Yeah, annoying because what this is useful for is this is useful for biochromophores, which are biological molecules that, for example, are fluorescent or interact with light. And you know I love me some fluorescence. So one example is there's a protein called you're gonna love this name, green fluorescent protein. That's the name of it. I
wonder
bet you'll
why
never
it's
guess
called...
what it does.
Let me guess. It's fluorescent and it's blue.
Yep.
Exactly that.
So there's this protein called green fluorescent protein, and it has a molecule in it that's responsible for the fluorescence. And he wants to study that fluorescent molecule using this.
Listen, I'll be honest. I am extremely biased here. I just want to know how that machine works.
Yeah, I'm trying to find it for you because he gave us a lecture yesterday. Because actually, in one of my modules, my professor is teaching about some of this theory, and so he's been teaching stuff in my module that I'm actually researching, which is very helpful.
The thing is, I've been wondering about isomers for such a long time. I've been wondering why they matter the way they do, and they're not just like an IUPAC naming thing. Only they apparently are a whole concept. And right here, there apparently is a machine that would answer that specific question for me, which would have been quite convenient. So this is it's just so cool. Wait, so is the whole point of separating them by isomers just for the sake of like ordering them?
I'm really trying to remember. I'm having a hard time.
Oh no, that's not what I mean. I mean like
I'd already had 3 hours of lectures before he.
Oh no, that's not what I mean. I mean like, do you separate them by isomers because of some like deep reason, or is it just like, oh, we just want to measure different isomers at different times?
I can't remember why as well.
Oh, I see. It's fine though.
Where is the thing? He showed us something, but it's not in this document. Where is it? Is it this? It's not this.
What application are you using?
Where
Discord?
is it?
Yes, we're using Discord. Discord has this cool feature.
Yeah, Discord has a whiteboard thing now.
The whiteboard thing is great, I gotta say.
Channels. Yeah, I actually love it.
Yeah. And
you can do it in text channels as well. You can just start it in text and then people can join it.
We have a whole thing down the bottom for like a future... For the PhD project right here. Right here is going to be for the PhD project.
Well, that was a PhD project that I was interested in. But I emailed the guy on Sunday evening. He hasn't replied yet, so I don't know if he's going to reply. Because ultimately, the uni I'm at is not like a super well-known uni. So when these people get someone from like Cambridge applying, they're always going to choose that person.
Yeah.
I'm trying to find where. It's just not here. He showed it in the lecture yesterday, and he talked specifically about separating this stuff by isomer. Bruh, I'm actually going insane. It's just
no, Flame, it's the big carbon again. They're trying to hide isomers from me. I'm onto something.
Left out half of the lecture.
Yeah, I'm onto something. I'm telling you, I'm onto something. They're hiding isomers now. First
Is
helium
it in
hydride,
the
now this.
resources?
Coincidence? I think not.
I'm looking for this. I'm gonna find this somewhere.
I really am excited for the chemistry video too, because it's gonna increase the chemistry audience, and then for any future live streams where you join in to like explain something, it's gonna be much more of a and I really like it, conversation wise. People who actually understand it instead of just me who's trying desperately. Oh yeah.
Oh, I'm so annoyed I can't find this.
You know, everyone, I've been thinking recently how about like caviar is the closest thing to mainstream eating of cum, you know?
What are you talking
what?
about?
No, don't mind me. I'm just what? Oh, I was just like conversation. Just I was just like making.
I stopped talking for 2 seconds.
I know. I was just thinking out loud. Okay. I don't. I'm a written for Kevin String. All right, yeah, the lynching. That's a great idea. It's the best sections.
Oh, I actually just can't find this. Oh.
It's fine. It's gonna be a mystery for a future make.
It's a really cool set of slides. I was like, yeah, this is cool. I'm definitely gonna look back at this. And, man, I'm so annoyed because he was like, oh, you separate it by this, and you close this gate, and it cuts this off. Like, oh my god, I actually can't remember. Let me find. Oh, good. I found a paper where they're doing it.
I'm surprised Make never noticed the war going on chat. I have noticed, it's just that, look at this, alright? Listen, the war in chat might have been a bit interesting, but come on.
Quadrupole mass filter. I know what that is. That's not the...
Such a wild thing to know what it is, I'll be honest.
No, okay, it sounds complicated. It just means, so you know when it says quadrupole, that just means it has 4 poles. And
no way.
Scientists are quite direct with this stuff. It has 4 poles, and if you imagine, I'm gonna draw this out for you.
Quadruple is like, was it fluorescent green protein? I gotta say, those names are much better.
So this is our quadrupole.
Right.
Imagine this is a square, and I haven't drawn it badly. Your ions travel through this, and so if you imagine that, then this is like a long tube. So I've done this is a cross section of a tube, right? So these poles are big long tubes. So you know, like this.
Right.
That's not blue. That's blue. Yeah. Anyway, so they're all traveling through, and our ions will, based on the mass of the ions, so the ions are going to be kind of going through this in like a spiral, because the ions are charged, and they're going to be attracted to some of these and repelled by some, and they're spinning around, but what this whole thing does is it only lets ions through if they have a perfect mass for the potential on these poles. Because if the mass is too big, then it doesn't get wiggled around enough, and so it kind of gets rotated too slowly, and it will either collide with one of the poles or it gets yeeted off out the whole thing.
So kind of like a semi-orbit? Am I getting this right?
Yeah, so it's like you need the perfect mass for it to be rotated, or perfect mass to charge ratio, sorry, for it to be staying in a stable like spinning formation as it travels. Because if it's too heavy, then it's not going to rotate enough and it's going to collide into one of these or get yeeted off. And if it's too light, it's going to rotate too much and collide or get yeeted off.
Yeah, so kind of like an orbit where you need to counter just right for it to stay in perfect orbit, because otherwise they're gonna fall and crash the ground or escape the...
Yeah.
Okay.
And so the effect of this is you're filtering by mass.
Oh.
So this is an alternative to time of flight.
Wait, mass or mass to charge?
Mass to charge ratio. Sorry, I always say mass, but mass to charge. Yeah.
No,
so
it's
this is an
fine.
alternative to time of flight.
Oh, makes sense.
So you can use this instead of time of flight. I think it's easier to use, but the downside is that obviously if your stuff is all colliding with these poles, then you have to clean them, because over time they're gonna like collect sample on them.
I gotta say, in my opinion, the time of flight is more elegant.
Yeah, I mean, I did rush through this, but I do think this is quite cool. I have to present this on Thursday. I have to do a presentation on mass spectroscopy, which involves time of flight and quadrupole mass filter. So it's it's quite funny. This is my presentation practice right now, I guess. So that's useful.
I love how you got the compliment for being good at public speaking, public presenting. Like, yeah. I know. Really shocking.
Really?
I had no idea.
What does it say? Electrospray ionization. That's a type of ionization method. So this is not electrospray. Electrospray. Let me pull up electrospray.
Is it
this
what
is
it
now,
sounds like?
Yeah.
Okay. I like it. I like it when chemists name things by what they are. It's like Brussels sprouts. That's exactly what they are. It's just lovely. Korean fluorescent.
I mean, electrospray is quite complicated. But today's stream has now turned into my presentation practice. So
this stream was hijacked by.
I mean, it's useful because the thing is, my thing does mass spec and it does ionization and mass spectrometry. Essentially, if you were to take my whole instrument and chop off the whole VMI section, this is a mass spectrometer. So my instrument is a mass spectrometer, but way cooler because it does extra stuff. So my presentation is on mass spectrometry. So I get to
mass
talk about...
Mass spectrometry is the way I understood this machine before you explained it today, actually.
Yeah. Okay. I mean, I could even pull up my presentation. Let me... I've put no slides on this presentation because it's not being marked. And so I was like, I'll just sit down for an hour and put some slides in. so I haven't... There's nothing on there. You're gonna laugh when you see it. Let me put this up. Do I not have the file saved on my PC? Is it in the cloud? It's in the cloud. OneDrive. Oh, it's not. I have to go on OneDrive on the web because it's a joint presentation, by the way. So my classmate, she's actually put effort into her half. And I have not put effort into mine. But I'm still going to present it better because I'm better at speaking.
That's just specializing. That's good.
What do you mean?
You know, classmate. Just
yeah, I mean, to be honest, I should have let her make the slides and me present. That would have actually been maximum efficiency. We would have popped off with that one. But that would have also meant I have to understand all of the stuff on her slides, which I don't, because she's a biochemist.
No.
Okay, I found the slide. Let me download it and then remove my name and her name, because I'm nice. Because I'm not going to dox her. How do I download? File. No, it's not in file because why would it be? I guess. My bad. How do you download this? You'd think they would just have a download button on OneDrive.
No, no, Windows hates it when, things make sense. There is like...
Save as.
I know it's a bit...
Download a copy.
I know
Okay.
it's a bit unrelated, but I yesterday realized that Microsoft actually released like apparently a new image editor. So when you have an image, you can just edit that image in that editor instead of Paint.
Okay.
And the thing is, each time you edit, apparently you need to like use the Microsoft currency thing, the one you got when they were testing out Bing. Each time you use Bing, you would get the currency. And like apparently you need to use these points to edit images, and that's such a Microsoft moment where you need to collect points in order to use their programs. I've already paid for the whole operating system. Just let me do this thing.
I'm just checking. She hasn't doxed any of us in these other slides. I think we're good. You're gonna tell that she's a biochemist because she actually cares about the proteins. Oh, by the way, the presentation is on protein mass spectrometry, but I obviously haven't talked about proteins.
I'll be honest. I don't know much about proteins, so but I
what
do
you
know
about proteins.
I know they exist.
Do you know what they are?
Proteins, right? It's kind of the extent of my knowledge.
Yeah, you're not wrong.
I am slowly going up from theoretical chemistry through organic and inorganic, right? Proteins are way down the line.
Okay, proteins, I mean, do you know that proteins are molecules?
Yes, I know that much. I also remember they're like chained to something, right?
Yes.
Yeah, that's kind of it.
Do you know what an amino acid is?
Deep within my mind, I think so, but I can't remember it right now.
An amino acid is like a small organic molecule. That it has like an amine group and a carboxylic acid group, so we call it amino acid.
Makes sense.
So it has a base which is always the same, but it has this bit on the end which is different, which will change from one amino acid to another amino acid. And so you have a bunch of types of amino acid where they all have the same base, but they have different bits on the end.
Okay.
And the thing with these bases is they will all connect together. They'll connect to other bases.
Oh, so protein is just a chain of amino acids, so that you can basically so the skeleton is always the same. It's always a protein, but then if you change up the acids themselves, like the endings, the acids,
you're changing up the endings. Yeah.
That makes sense.
Exactly. And so a protein is like a big skeleton, a big chain of those, and depending on which bits you've got on the ends, the whole chain will fold up into different shapes and do completely different things. Did you see the recent Nobel Prizes?
I do remember a couple months ago, I think it was, when you joined in on stream, you did ask me about proteins. I had no idea what they were. And then you did also mention that it's like one of the recent Nobel Prizes had something to do with proteins.
The Nobel Prize was announced like 3 weeks ago or something in chemistry.
That new? Oh, I have no idea.
Yeah, so the Nobel Prize in Chemistry for this year was this thing called AlphaFold. Have you heard of it?
I think so. Wasn't it like the AI that actually could simulate... Wait, was it simulate all proteins or predict all proteins?
Predict. So what AlphaFold does is you give it this chain of amino acids. So the protein, we call it protein sequence. You give it this chain of amino acids, and AlphaFold then says, this will fold exactly this way to make this shape of protein. So it's telling you how the chain is going to fold up on itself.
Yeah, it was like insanely accurate too, wasn't it?
Yeah, it's really, really good. I used it last year. So I had to write a report on
the thing is,
protein
it used to be insane to use AIs for simulations, and the fact that right now something like AlphaFold exists is just wild.
Yeah. And the thing is, previously, for chemists to predict the structure of a protein, they had to spend years like working on it to either figure it out experimentally or to predict the structure based on other proteins and piece it together one by one and do a bunch of simulations.
Yeah, the thing is, I really cannot stress enough how impressive though it is that AlphaFold is accurate, because
Yeah.
asking AlphaFold basically how a protein will fold is kind of like having that one weird wizard friend and then basically asking him, and he just based on his feels, like guessing how it would
Because it
fold.
just sees these patterns that we can't see.
No, the thing is, it's not even like seeing the patterns. It just has a feeling it would fold
Yeah,
this way.
yeah.
And
It just sees a trend. It's like, oh, well,
yeah, it's
these past
basically
ones did this, so this must do
the
this.
thing is, it from a computer science point of view, the closest thing to how an AI like this would function is literally just a human guessing.
Yeah.
Like, for example, for us humans, it's obvious how we need to balance our center of mass in order to stay up. But the thing is, balancing your center of mass with 2 legs and 2 arms is actually an insanely difficult task. Boston Dynamics has been working on it for how many decades at this point? But we do it just based on feels and with no science behind it. And AlphaFold is just guessing it correctly. It's incredible.
Yeah. You can show this on stream because I've cleared all the doxing potential. I had to make sure you see the top right, my like account. I had to switch my account because it had my initials.
Oh, I'm just covering it. I'm just covering it up with the whiteboard.
Oh, it's fine. It's fine.
Just in case.
Anyway, I'll put it in present mode anyway.
Presentation.
That's not doing it right. That's terrible. I'll just go through this. Okay. Anyway, so you can see my slides are terrible. I've literally just I put the whole thing on here and I've just made it bigger. But you can see I've put in my pictures as I've cheated basically.
Too bad. Could be. It's not.
Yeah.
Worse.
And this is
that's the
did I show you? This is the time of flight detector.
Yeah, I
that's
remember.
Going in my machine.
I remember we talked about it one stream.
Yeah.
And like you 3D printed the one part of it too.
Oh yeah, the blue bit on here is 3D printed. And then you can see that this is where my friend's stuff starts, and this is all proteins. So this is the protein chain, this blue thing.
Mm-hmm.
And what she's showing is you can replace hydrogen atoms on here with deuterium atoms. This is the amino acid chain. So this R on here is that extra bit that changes. Right?
Oh.
In chemistry, when we say
That makes
R, we
sense.
mean an organic thing that can be anything.
Yeah, I think we've
But this
stood
is the
for something.
repeating base. This whole thing is the bases.
Wait, did she make that graphic?
She found it somewhere and just pasted them all.
Oh, I see.
It's not plagiarism because this isn't
Quenching.
this isn't graded.
I'm guessing that's an actual
Quenching.
term for.
Yeah, quenching is
You'll
this is
have a-
another way we draw proteins. We draw these loops for certain sections of proteins and these sheets for others because they flip flop back and forth to make a long thing.
Yeah, I think I remember seeing this notation somewhere. Or just wait 30%.
And she's just talking about all of this. She goes quite in depth. This is another way we show proteins. This is literally just the whole thing after it's been folded, so it's just a massive molecule, basically. And some of the ways it folds is, do you know hydrophobic and hydrophilic?
Yeah, hydrophobic it basically don't like water. Hydrophilic loves water.
Do you know what they mean in terms of molecules?
It was water polarity, wasn't it? Don't remember exactly. Wait. Hydrophobic. Yeah, I don't remember exactly what of water polarity. I'll be honest.
So, do you know what makes something dissolve in water?
Not quite. That's kind of the pre-issue.
If I ask you, will a polar or a non-polar molecule dissolve in water, which would you say?
Polar?
Yep.
Okay.
And that's because if you imagine the water molecules, they're all polarized, right?
So they basically like attack it.
Yeah, so they'll stick around it. If there's a positive part on a molecule, then all the oxygen ends of the water will stick to it. If there's a negative part, then all the hydrogen ends of the water will stick to it.
Makes sense. And they have an easier time to do it with a polar molecule than the
it
non-polar one.
stabilizes it basically. Whereas if you have a non-polar molecule, water doesn't like it very much.
Has nothing to stick to.
And that's something like oil. Oil is the most obvious like non-polar thing ever. And most non-polar molecules, we might call them lipophilic sometimes. Lipophilic and hydrophobic mean the same thing, but lipophilic just means likes fatty molecules. And when we say fatty molecules, we mean things with long carbon-hydrogen chains. Because I don't know if you know, but carbon-hydrogen bonds are barely polar at all. There's barely any electronegativity difference between carbon and hydrogen. So that bond is
Makes
just
sense.
not polar. And so when things have these long carbon-hydrogen chains, it basically means the whole molecule is just not polar at all.
Makes sense.
And so oils and things have a lot of carbon-hydrogen chains. That's why like petrol and stuff, it's all oils. They're all hydrocarbons. Okay, back to proteins. Proteins, some of the R, the R groups, I said, the bits on the
Right.
end.
Yep.
Some of those R groups can be polar or non-polar. And, in your body, most things are dissolved in water. And so what happens is the protein will fold in such a way that in the middle of the protein, you have all the non-polar stuff. And on the outside of the protein, you have all the polar stuff. And that really stabilizes the protein. That really helps it keep its shape because all the non-polar stuff wants to stay away from the water in the middle of the protein, and it's all shielded by itself. That it's all
Makes
grouped up
sense.
in the middle,
Makes sense.
and we call it a hydrophobic center. Whereas on the outside, the water is stabilizing that. It really wants to be in contact with water. So yeah, that's some stuff about protein structure, just to put some more context on it, and also tie in like how it connects to other chemistry. Like polarity and stuff. Everything's connected. That's what I like about science. Yeah. Yeah. Okay, I went on a big tangent. I've been yapping. Oh my god. Is it too much for one day?
I don't know. I'll be honest. I mean, here's the thing. When I started this stream, I was expecting it to be a complete flop because, I'll be honest, I haven't been feeling too great. And then later on, and I specifically haven't drank any coffee because later on I have a video to finish. So I wanted to save up all of my caffeine reserves for that. So I was expecting it to be a complete flop, but then you joined in and you just started just showing me all of these awesome things, and now I'm ready for them all. I'll be honest.
I mean, I can go through some of the mass spec stuff because explaining it to you will help me present it. Honestly, I need to learn more about these inlets. I think they don't do much. I think it's literally just this is our way of getting the sample from the outside to inside the machine. And the whole machine is in a vacuum. So I said high vacuum here, but that's because this bit needs to be high vacuum, whereas the rest of it is just normal vacuum because we still want it to be like not many other molecules interfering. But here is where it really matters because this is where we're separating by mass. And this is where we're detecting. So if you have any other molecules, they're going to mess up everything.
Makes sense, once again.
And going back to like my instruments, the entire of my instrument needs to be high vacuum. Nothing can be low vacuum or anything. And that's because it's super sensitive. I don't know if you can see in any of the pictures, the pictures with the blue circles. You can see some like dots on the sides. And that's like random noise, basically.
Yeah, I was actually wondering if I was gonna ask you if those were like electrons that something weird happened to them, or if it was just noise.
Yeah, he didn't really say. I was curious about what causes the noise. If it's like background radiation or just electrons coming from just anywhere, or if it's molecules that have found their way into the machine. But it wasn't really clear. So I'm not sure what actually causes them.
Actually, how are
But
those
we just
electrons
remove
detected?
the background from the full spectrum.
How are the electrons detected, actually?
What do you mean?
Like, what mechanic is actually detecting them? So right here, when an electron hits this, it's somehow...
I think it's a... actually, I can show you on the slides. Yeah, I think it's just another one of these. I think it's pretty much the same thing. So we use what's called a microchannel plate, which I think I explained to you. Did I explain this to you?
I don't actually remember this one, I'll be honest.
Okay, so this is like a... So this microchannel plate is this thing here, this black bit, and it's like a bunch of really tiny tubes. And what happens is when the electron hits the inside of these tubes, it produces more electrons. And then those electrons hit the other side of the tube and it produces more electrons. And then it hits the other side, it produces more. And so what happens is each of these tiny tubes, if any of them picks up one electron, it then produces a bunch of electrons coming out the other end of the tube.
So it's basically like an electron amplifier.
Yeah, it's an amplifier. And then a scintillator is a material where an electron hits it and it releases light. And so this scintillator is.
Oh, I remember the scintillator part. Yeah, I do remember you mentioning the scintillator part.
Okay, it's getting all these electrons, it's releasing light. And then photomultiplier, I can't remember how it works, but it essentially does what this does. This is just.
Photomultiplier, I mean, it's in the name.
Yeah. And this stuff is really expensive because this is how night vision goggles work. And night vision goggles are expensive because the military wants them.
Oh, that makes sense, actually.
So, yeah. So night vision goggles are photomultipliers at the heart, but I think they convert photons into electrons, do this stuff, and then convert it back into light.
I'm actually.
I think the reason they're green is because they have like a phosphor.
White phosphor, I'm not mistaken, that's what they're called.
Yeah, they have like a screen at the back that detects, it receives the light and amplifies it green.
There's one
it's like green fluorescent
thing I'm curious about because on the Wikipedia page right here it says is used to detect single particles, electrons, ions, and neutrons, and photons. However, I am curious about the way it actually operates because that could just. Oh yeah, it's gonna be good when these are the names of like different parts. Yeah, that's how you know it's gonna be good.
What did it say?
Einfallendes Elektron.
Nein. Einfallendes Elektron.
Sekunde Elektronen.
Elektronenschauer.
Say what you want about German language, it probably would be the best language to do science in. Like every single word, every single complex scientific word, it's just gonna be literally what it is.
Yeah, my basically supervisor for my summer project, he was German. And so he would sometimes not know the English word, and he'd say some German word, and it would be like a really long combination of like 4 different words.
Yeah, because
they're all science words, so they just shoved all the words together.
I mean, this is actually pretty genius. Instead of saying stuff like, what's some sort of annoying word to memorize? Like, I don't know, instead of calling it spin, they would call it the quantum number 4 of the electron. It's so much easier.
Yeah.
I'm curious how it works because I know why I'm going this much of a tangent. Particle photon that is one chance more guaranteed to hit the walls of a child due to a child being at the negative plate. This impact starts a cascade of electrons that propagates. Oh, so if something hits the back of it, then electrons fall off?
If it hits the side of it, the electrons get knocked round to the other side. So like if you imagine it's a tube, but everything is coming in at a slight angle, so everything that hits the inside of the tube will produce more electrons that then hit the other side of the tube, which produces more. So as it goes through, it bounces around a bunch of electrons that eventually come out the other end of the tube.
Actually, funny enough, examples of use. The mass market application of microchannel plates is in the image intensifier tubes of night vision goggles.
Yep. Oh wait, it says at the bottom, the third one, MCP detectors.
Physical research, they can find devices as electron and mass spectrometers.
Yep.
Really? No way! I had no idea. Flame, this just sounds like something you could actually use.
Yeah,
you should probably look into that.
Yeah, so these slides are just random bullet points, which I'm just going to yap about, because I just put bullet points in. I was like, oh yeah, I'll just write a script to talk about. I mean,
to be fair, that is the best way to talk. Like, for example, when I write script for my videos, I just say things out loud when I'm scripting them, and then just note down exactly what I'm saying. Because for most things, you don't really need a script. You can just yap.
The problem is, on these slides especially, I haven't given people something to look at. Because one of the things with presenting is, obviously you don't want to read off the slides. You never put a bunch of text on the slides, but you put images on. So I think this is a good thing. This is a good one.
Do you have the time
Because you
to
need to give people something to look at while
actually
you
wait?
talk to them.
When will you give this presentation?
On Thursday, but I'm doing a practice with my friend tomorrow.
Oh, so I mean, for the inlet, can't you just take a picture of the from the machine?
I mean, yeah, but the picture. I mean, you can see part of the inlet on here. I have no idea what's going on there. I don't think anyone will. So it's not going to help.
There's an inlet. It's silver, as you can see. Pretty,
Yeah,
beautiful,
and I don't
very
even know if
nice.
this is the inlet. You know, like there's this whole thing here. I've got no idea what's going on.
Just an image. So yeah, this is probably the inlet.
Yeah.
As you can see, it's round. It's silver. It's well, it has a bit of plastic at the bottom there. Pretty neat, pretty nice. It looks pretty good, pretty solid. Did I mention it's a cylinder
all
already?
these plastic things, these white bits, they're all pressure gauges.
Well, it makes sense. Vacuum.
I think these are pressure gates. So this is a vacuum pump, and there's a gate here. This is obviously going to be connected, and so these gates you can just open to pressure. Yeah.
By the way, I mean, yo, I can't follow on the stream right now. Stay strong, you're the best man of mathematics. Thank you. Funny thing to mention right now as we're talking about theoretical chemistry.
Yeah, this is lots of maths. Yeah.
I don't want to be known as the maths guy. I want to be the science guy. Bill Nye. This is really awesome. I can't stress that enough.
I'm really glad I got to draw a color-coded diagram. I'm not gonna lie. That's always my dream when I'm trying to explain something to someone.
That's the thing you want. That's the dream.
That's all I want.
It's the entire reason
I need to just carry 5 different colored pens with me anywhere and a notepad.
That's the entire reason I actually started researching everything, is because I just wanted a diagram.
You know, my mum's wanted to get me a laptop for my birthday. Not for my birthday, for Christmas. Because it would be useful for uni. But I've been telling her I don't want a laptop. I want a hybrid tablet laptop because I need to be able to draw stuff on it. I need to like carry a tablet. Can you imagine the sheer power of me with a tablet where I can just color code my pen and just draw? I would be unstoppable. I'm not gonna lie.
Yeah, I mean, spin, watch out. That would be spin explanation in 15 minutes.
Do you know much about like tablet like devices? Because I've been trying to look for something to get for Christmas.
No, I don't know. I only know like the typical normal things.
Okay, because they do like these. They're called tablet PCs now, which are like tablets but with Windows on them, and they have like a keyboard that you can just click on with a magnet onto the bottom, and so it's like you can carry it like a tablet with Windows on it. But then you just pull out the keyboard, snap it on the bottom, and it's a laptop instantly.
I mean, I'm pretty certain you can also like just buy keyboards for tablets.
Yeah, you can, but those tablets don't have Windows, and I need a tablet with Windows because I want to actually do uni work on it.
That makes sense.
So yeah.
Have you ever thought about learning Linux? And then the whole sell pitch on Linux.
I have to learn enough right now. I have to learn all these simulation things. I have to learn LaTeX. Do you know LaTeX?
Oh, I love LaTeX.
I have to learn it.
Oh, I use it so much.
All I know is LaTeX notation for like equations. I can do that. I've used it before, but I haven't actually used LaTeX.
I mean, it's not much more complex than that, actually. It doesn't get much more complex. The thing is, LaTeX... What do you mean exactly when you say learning LaTeX, actually?
I have to write my entire master's thesis on LaTeX.
Wait, on LaTeX? In LaTeX?
In LaTeX. As in something that uses LaTeX notation.
Oh,
because
that should be fine.
Because my supervisor, he's like, oh yeah, if you were a physics student, it would be mandatory for you to do this, so you don't have to, but you really should. And so I want to. I've only started writing on Word because I needed to get something on paper, and I wouldn't. If I were trying to do it with LaTeX, I would spend way too much time procrastinating.
I mean, the thing is, LaTeX is... Well, I've started using LaTeX in Manim, then I kind of use LaTeX in Docs. Google Docs doesn't quite use LaTeX. They have like their own modified version, which it makes it quite awful at times, but it speeds up a lot. There are moments where it's quicker for me to note down a complex equation in LaTeX than to draw it in Paint, because it's just
I mean, have you heard of Obsidian?
I love Obsidian.
Yeah, I use Obsidian for like.
Oh yeah, they also have LaTeX, yeah.
And that has the LaTeX notation for all the maths, so that's what I use. That's how I know the notation.
LaTeX is such a great thing. If I'm not mistaken, LaTeX is just like it's like a software renderer, I think they made, and then they made it really easy to connect to anything, and so now like all programs are just using LaTeX specifically because of that. Yeah. I went out of my way just to get an add-on to Blender. Let's see on the stream. Actually, I have it open, so I might as well. I went out of my way to get an add-on for Blender after they made the add-ons more annoying to add, which is just LaTeX to Blender, where I can just do, Oh wait, hold on. Oh yeah, that's the annoying part. One annoying part about LaTeX is I have no idea why, but apparently the dollar notation is different from this one, because if in this one you do this kind of equation.
Different to Obsidian?
It's not different to Obsidian, only in LaTeX the dollars, you'll see what I mean in a second. So right here to inf t and then f of x dx, whatever. If I compile this as mesh, then you will see this is what the equation looks like.
Okay.
However, if I replace these backslashes and square brackets with dollar signs like this, and then render it again, if I'm not mistaken, there we go. As you can see, it's different.
Oh, yeah.
Yeah, and that's
because it's trying to do it in line. What if you do $2 signs on each side?
Actually, yeah, if you do $2 signs, also different. If you remove dollar signs, also different. Yeah. So that's yeah, $2 sign still works.
That's because the single dollar sign is trying to do it in line, like in line.
Yeah, but what's quite silly is that there is no line here, is there?
Yeah, but I think that's logical. I think that's fair.
Yeah, I mean it is logical. It's just that you have no idea how many equations I screwed up, simply because it's really intuitive, but what's sometimes annoying is that the way it's intuitive, it goes out of its way to be intuitive. So for example, right here...
it follows its rules too strictly, when sometimes it would be better off just not following the rule and making it...
quite the opposite. Simpler. It's too intuitive, that's what I mean. It actually goes against the rules to make it easier. So for example, right here for the integral, if you want to add an negative infinity at the bottom, then you do the underscore, and then at the top you do the up arrow. However, normally what this would mean is, like for example, if I do an A, if I do underscore A and up arrow B, for example, and then if I compile it in line, like so, then you can see that the AB, actually no, it doesn't, never mind. I think like that's only works for inline, not this way. Or am I an idiot? Never mind. There was some way to do it where basically it would render the, or maybe it was with limits. I think it was with limits, where basically it would do the underscore in a completely different way. So limit underscore x right arrow B. Yeah, inline it breaks completely. If you do it with $2 signs. Never mind. Oh, I said lin, not lim. I gotta give me be patient with me. I have some serious problems. Limit? No, never mind. There was basically some way to do it so that the x to b was underneath the limit, but that only works for limits. Unless I'm almost there. Just give me a second. Be patient with me. I'm not great with LaTeX. I know that I mentioned that. I just use it a lot. There we go. Now it's underneath the limit. But that's the... So basically, if you do this, if you add the backslash to a limit, it's gonna render in a different way than with the limit itself. So
Okay.
backslash to the limit, then the underscore changes its meaning.
Right,
And
because
that's
it's a different limit symbol, basically.
yeah, which I don't have a problem with that. Obviously, it looks different. The thing is, though, the underscore changes its meaning. So now, if you want to do a limit a like this, so have the same limit except with a letter down here, like so, I don't think you can,
Yeah.
because the limit will interpret the underscore as being underneath the limit, unless you add another underscore, maybe. So it is extremely intuitive. It's just that you have to not think about it too hard, because then it isn't.
Mm-hmm.
Yeah, and it worked because, as I mentioned, it is intuitive, not logical, but well, quite logical. It's just at times not logical, but extremely intuitive. So I don't think you have to worry about that. Just Obsidian, just use it a whole lot. LaTeX is great because it's everywhere. It's so amazing to have a standard for this. It's also used for chemical reactions, for organic chemistry. There are also packages I've seen. What's so nice about this?
You mean for Obsidian or for LaTeX?
LaTeX. So if you learn LaTeX, you can use it everywhere. Manim, Obsidian,
Okay,
Blender, Docs, absolutely everywhere. And then even if you can't use it somewhere, then someone probably made an add-on so that then you can import LaTeX.
Because Obsidian has
By default,
I can pull up Obsidian. Obsidian has a bunch of plugins for chemistry.
I absolutely love that about Obsidian. They just made a framework, if I'm not mistaken, for people to make plugins. And so, because of that, the thing is, it's not even that Obsidian has, it's just people who do chemistry and, can do some extremely basic programming, make add-ons to make their lives easier, and then they just make them open source. And I absolutely love it. Why is there a potato? No, those are obviously electrons. Duh. Have you never seen electrons represented this way, Greg? Everyone knows these are electrons. And that's how you represent them. Hide the ground, by the way. Oh, hide the...
Have a look at my Obsidian.
Hide the LaTeX person down.
If I find... Where is... amino acids. Here you go. I've got all our amino acids here. And if I switch to reading mode, you can see it puts the thing in Obsidian.
Oh, those are banging notes. Wait, what do you use to note down these molecules, actually? Like in editing mode.
It's a... Where is it? Community plugins. I think it's this. It's Chem. This format is called Smiles, because you do this certain string. You have to learn how to do it. You see this? You have to write these out, and then it converts these into a molecule.
Yeah. So what I meant is that in LaTeX there is a package called Chemfig. There's a package called Ochem and Streetex and Zimtex or Chemtex. Oh, Chemtex. I get it because LaTeX. That's funny. And all of them just allow you to do molecules except in LaTeX. Oh, never mind. There's even more.
You can see here. I've got a group of hydrophobic ones, and so you can see this is the amino acid section, but then the rest of this is all hydrocarbon. This is a sulfur, but it's sulfur. It doesn't matter.
I gotta say, these are absolutely banging notes. That's extremely well done.
And the aromatics are especially hydrophobic, except this one.
Oh, but wait, it would make sense, unless I'm wrong, but it would make sense for benzene to be extremely hydrophobic because, well, it seems extremely well distributed.
Yeah.
And hexane, was it? I think.
Hexane, yeah, benzene without the double bonds.
Yeah, hexane also.
Oh, sorry, cyclohexane.
Yeah. Cyclohexane, right?
Yeah.
I knew I was missing something.
Hexane. I've got a bunch of random molecules. Let me go to the. I stopped using this for all my notes. Oh my god, where did the thing go?
Absolutely love this feature. This is such an ADHD thing to have, by the way.
I love the way they just bounce around.
Oh, you can throw them around too. That's also great. It's such an
How do I sort this by groups? Yeah, molecule. Okay, so all the red ones are molecules. I sometimes just find a molecule, I just draw it in. Like I've drawn caffeine in here for no reason. And you can just see this caffeine in there. What other ones have I drawn? Grignard reagent. I haven't even finished this. There we go. Okay. 3-pentanone. Like I don't even know why these are in here. What is it? Why? What? Oh, this is for catalysis. Okay.
What even is that? That's a cursed molecule. Oh, those aren't real. There's no way. Those are not real molecules. Those are so.
This is.
Okay, no, remember a while back when I was learning the IUPAC?
Cyclohexane.
No, finally something. Remember a while back when I was learning like the IUPAC naming thing for organic molecules?
Yeah.
The things you're showing on the screen would have killed me. Still would kill me right now.
I'm not the best at IUPAC, I'm not gonna lie.
Yeah, because I mean the naming is. Okay, that's something I can name.
Research. Do you remember this propyl alcohol?
I do remember it somewhere. Yeah. I don't remember what
this stinks. This is terrible. It's got a toxic smell, and that's because it is toxic.
Isn't that the one where like it was lethal, and then you could smell it, and then you were like, oh, once again, extremely silly molecule.
Yeah.
I just want to make a tier list of molecules by how silly they are.
Yeah, I put R's on these for like.
Wait, why is the? Hold on. No, you okay? Well, for that molecule.
Fluorescence here. Fluorescence. Oh, I missed this.
J plus K. I know what this means. I think. No, do I? Never mind. No, I don't.
What is this connected to? Jablonski diagram. Phosphorescence. Okay, this is the triple energy. Okay. I miss Obsidian. I need to start using it for my notes again because I actually missed this.
I absolutely love Obsidian, and it's such a shame that I can't use it for anything because I don't have to take notes. There's one thing I really want to do. Oh my goodness, it's such a weird thing to enjoy, but I really like making documentation and documenting things in general. The only problem is I am not like an expert in anything. And because I don't get to document stuff often.
Right.
Which is a problem. But recently I bought SolidWorks, and right after I finish this video, I really want to start using it, learn how it works exactly, and I really want to start making stuff, finally. Every single time you just show me something, I just get this itch. I just want to make stuff.
You just want to make it.
Yeah, I just want to make it. I want to make it happen.
These are the partition functions. Do you remember these? This is statistical thermodynamics.
Oh, I do.
Because I started using Obsidian when I was learning statistical thermodynamics, so I just made a bunch of equations. You can see it. And here I use the double dollars because if I didn't, then it would have done it small. So that's your issue. I've been there. There we go. Yeah, I miss these notes. I really need this like laptop tablet thing so I can start doing this again. Because the problem is I study better like in the library at uni. So that's where I study. But that means that I can't do Obsidian notes because I don't have a laptop. And Obsidian, I can't, do it on the library computers. So I just haven't been taking notes on Obsidian. Which is a shame.
Oh, just remind me of another fun thing I want to do, note-wise. That's a bit of a...
this was insane. I remember that. This is my coursework.
Whoa, what? No. Hold on. You're just gonna gloss over? Why? Just why? Why? Why so many? You know what I absolutely love right here when you have these equations? I absolutely love it how clean the equations are with just the the constants in them or the values, the symbols,
Yeah.
and then the second you actually try to calculate anything,
Yeah.
it dissolves into complete mess.
This was wrong as well. I got this wrong.
I mean, considering how what the equation looks like, I don't think a human could get that right.
This was my favorite part of the whole thing. This is like allowed transitions. This is like triplets and singlets, whether they're allowed or not. For the transitions in fluorescence and phosphorescence. Yeah, because they gave us these molecules and they're like, "Oh, analyze the fluorescence and the absorption spectrum." And this is this is when they absorb photons. This is where they absorb them, and this is where they emit them. So you can see they absorb photons at this energy, at this wavelength, and then they emit them at a lower wavelength. Or sorry, a higher wavelength, which means lower energy.
Makes sense.
What is this? Okay, what? Oh, this is a lot nicer if I can just click through it. Yeah, I did all my coursework on Obsidian, and then the deadline was in like an hour, and I was like, oh, it's fine, I'll just convert it to Word. Converting this to Word was a nightmare. What I ended up doing was I spent an entire like 50 minutes trying to convert this to Word. I only did half of it in that time. And so I just took the Obsidian file, converted it into a PDF, and just uploaded that with all the colors and everything. so they were looking at it like, what the hell is this? But you know, it was good enough.
Also, I like Greg saying, "Make it. I'm on mobile. I can't read that. Please copy everything into the chat. Thanks." On it. That was great. So cool though. I think that might be it for me today. I
think I've done enough yapping.
I mean, don't get me wrong. I would love to continue. It's just that I have stuff to do.
I need to prep for my presentation.
If it was like weekend when no one actually gives me anything to do for the weekend because for some reason they actually want on the same day most of the time, then I would just sit here for hours ready to hear the yapping. But unfortunately, it's the society. It's the big carbon. Big carbon's plan. Anyhow, thank you so much for joining.
Thank you for having me. It was
really great.
Really good like presentation practice anyway, like explaining this stuff.
Whenever you and also if you were to like find the slides or just figure out how the isomers machine.
I'm gonna ask him about them.
Yeah, then I'm just saying, if you were to like stumble upon them, it's not that I need to know. It's just I'm not saying.
I also need to know. It's really relevant. I don't know how he couldn't put those slides up there. Like, yeah.
Well,
he's gonna be mad that I forgot how it worked, but
I'm
just gonna say I'd already been through 3 hours of lectures on that Monday morning, and that was when he explained it, and that just did not stay in my head.
Or you can just hide it like, oh, I have this friend who wants the slides something, and be like, oh no, it's not for me. I know how it works. Of course I know how it works. I've been listening to your lecture, of course. I just need it for that guy who was curious about isomers. You wouldn't be lying.
Yeah, but also legally I can't share the slides.
Well, I suppose that's a fair point.
Yeah.
It wouldn't be embarrassing. It would be just illegal.
Yeah.
Could be worse. Anyway, I'm gonna go now. Thank you so much.
Yeah.
For joining.
Thank you. I'll be back whenever.
All right.
Actually, I'm going back to London from Thursday to like Saturday, so I won't be back then. But maybe some other time.
Whenever you're free, whenever you have anything to show, I'm always glad to listen.
Yeah. I just find all this stuff like really cool.
It
so
is
I just
really
always
cool.
need to talk to someone about it.
It is really awesome.
You're at the perfect level to understand the stuff I explain without knowing so much that you find it boring. You know, like, like if I'm talking about this to my classmates, they're like, oh, it's just physical chemistry. but to you, you actually care, you know?
Yeah, it's so fun because like on one hand I really want to learn about this, but on the other hand you really often just say things which are absolutely obvious to you, like not even a fact. This is just like something that's a given, and I'm like, oh, what does that mean? Yeah, so we know what proteins are. Well, let's just assume that I don't for a second. A transition states or whatever. Well, anyway, I really should get going. Thank you so much, Flame.
Yeah, thank you. When are you posting the chemistry video, by the way?
I think tomorrow, like 7 a.m., maybe 12 a.m.,
Okay.
12 p.m. I mean,
Right, I'm looking forward to it.
all right. I hope I won't disappoint. I really
You
hope
never
so.
do. Like, I'm never disappointed.
Yeah, but the election video kind
I
of
sometimes
sucked.
think, oh, I should have maybe mentioned this to him because it would have been cool to talk about or something. But
Yeah, but
that's it.
I really screwed up the Electron video because I started with basically I wanted to segue in really smoothly into theoretical chemistry. I really wanted to hook people in with the physical aspect of it being a particle, but it just didn't work. I really hope this time will be more interesting. Anyway, see ya.
Yeah, bye bye.
And for now, that'll be it. Thank you everyone so much for watching, and have a great day. Bye.